Okay, thank you for coming back to me safely from spring break. You may notice I have a limp because I broke my foot the Sunday starting spring break. So my walks on the beach were very short and painful. But I did actually go to South Padre with my wife. We celebrated our 31st wedding anniversary. And so we had, thank you. Same person even. Yeah. But so it was really nice for us to leave our teenage kids at home, just head down there. Wasn't too crazy down there because it was kind of cold. So, but we heard a couple raves here and there. So it was definitely fun. But anyway, getting back to this, we're going to finish up chapter 6 and start chapter 7 today. We'll finish chapter 7 and have time for review on Wednesday. Okay, and then our test is next Monday. Okay. Now, you should have all gotten an email about 2 minutes ago that said we're going to start restricting. I am going to start restricting quizzes and exams taken online to be only between 11 a.m., which is when this class starts, and 3:20 p.m., which is when my other class ends. So you must take it in that window. If you have been taking it outside that window, plan ahead and take it inside that window now. There's been some unusual anomalies for people, especially the late at night crew. So I've decided to restrict it for that much. But other than that, I think overall it's been working out. Okay, so let's remember what we were doing. Okay, we started out with SN1 and SN2. These two reactions can make all these different functional groups depending on what your nucleophile is. Okay, now those are substitution reactions. We're going to talk about a different reaction today, and it's called an elimination reaction. In an elimination reaction, we're going to remove something from one carbon, and we're going to remove something else from an adjacent carbon, okay? Most of the time, we're going to remove a halogen and a hydrogen, so we call it dehydrohalogenation, and we can use a strong base to remove that acid from the system. So we're going from 2 sp3 hybridized carbons to 2 sp2 hybridized carbons, and we're gaining a pi bond, okay? So we're losing 2 sigma bonds and we're gaining 1 pi bond to do this, okay? Note the hybridization of the different carbons are changing and therefore its shape is changing, okay? So this is the general reaction here. We'll see that when we have this system, I found my Apple pencil, by the way. When we have the system, we'll have one leaving group is on one side. This is typically the halogen. And then we'll have something else on the other one. And what we're going to start with talking about is that's going to be a hydrogen. And so we're going to lose a hydrogen on one carbon and a halogen on the next. Okay. So we call this dehydrohalogenation. Okay. We're going to lose other things too, but this is what we're going to start with. In dehydrohalogenation, we're going to move that hydrogen from one, and then we're going to move the halogen from one carbon, giving us our pi bond. Now, we have to define the carbon that has the halogen on it is what we call our alpha carbon, okay? Alpha carbon, it has the leaving group on it, okay? So it has the alpha carbon. The other carbon is what we call our beta carbon, okay? That beta carbon is directly attached to it, adjacent to it, and it has to have a hydrogen on it for this reaction to work, okay? So when we have that, we have these hydrogens here, and we call these beta hydrogens, okay? So whenever you have this elimination reaction, you're gonna look for the leaving group on your alpha carbon, and you're looking for beta hydrogens, okay? And that's why we call it a beta elimination, okay? So we're gonna use the electrons from the hydrogen here to build our double bond, and the electrons from the leaving group here are going to leave with it, leaving with the leaving group leaving as a negative charge, okay? So that's where the electrons are flowing this. The hydrogen electrons are kicking in to form our double bond. Our leaving group are pulling out its electrons to create our negative charge. Okay, questions on that? Okay, so dehydrohalogenation, removing a hydrogen and a halogen. Okay, all right, so there's 2 ways to do this. Obviously, if there's an SN1 and an SN2 for substitution reactions, we're gonna have 2 different ways to do this. It's gonna be an E1 and an E2. And they're similar in the fact that the E1 means unimolecular. E1 means carbocation. Okay. E2, like SN2, is bimolecular. You have to have the base in the situation pulling the hydrogen off before you have the reaction happen. And so it's bimolecular. So it uses the same terminology as the substitution reactions, except the E stands for elimination. Okay. So the difference in this is the timing of our bond cleavage and formation. So like I said before, E1 gives you a carbocation, SN1 gives you a carbocation. E2 does not form a carbocation, SN2 does not form a carbocation. So they're very analogous in that comment. So they have some common features between them, okay? But the first thing we want to do is we want to make sure that we're removing the right hydrogens and forming our double bond in the right place. So when we do this, we have to find our alpha carbon, the one with the leaving group on it. In this case, it's always going to be a halogen when we're talking about dehydrohalogenation. Then we have to identify all the possible beta hydrogens, okay? There might be more than one. If you have, like in this case here, we have the possibility of a beta hydrogen on this carbon here, but we also have beta carbons on hydrogens on this carbon and beta hydrogens on this carbon. So for this particular one, those are all equal. And so it doesn't matter which one we take it off. And when we remove one of those beta hydrogens, we're going to end up with our elimination product here. Notice what we use to do this. We're using sodium hydroxide. We're using a base. Okay, we're using a base because we're removing acid from our hydrocarbon. And so the base is what's going to basically neutralize it and get us to our final product. Now, let's look on this one down here. We have two different beta carbons right here, but they're not exactly the same. Okay, because this one has 3 hydrogens on it. This one only has 2 hydrogens on it. I'm sorry, let me draw them in different things. The one right here on the right here only has 2 beta hydrogens. The one on the left has 3 beta hydrogens. So they're different, okay? And then notice we're using a different base here. This base right here is T-butoxide, okay? What do we call T-butoxide when we were talking about substitution reactions? A non-nucleophilic base. So all it can do is act as a base, okay? And it's really big. So we have to start thinking about sterics when we have T-butoxide. So we want to look at that. Okay, so in this case here, if we eliminate the beta hydrogen on the left side here, we're going to end up with this alkene at the end of the chain. If we eliminate from the one with just the 2 hydrogens, we're going to have an internal alkene. It's not at the end of the chain. So you see, you get 2 different products depending on which beta hydrogen you remove. So when we do this, we have to have some rules that'll help us decide which one it's going to remove, okay? So let's look at this mechanism here. I said it was a bimolecular mechanism, okay? So what we're having to do is we're having to have our base come in right here. This is our base, OH right here. It's going to use its electrons instead of acting as a nucleophile on the alpha carbon here. It's going to use its electrons to pull a hydrogen off the beta carbon. As it's pulling that hydrogen off, then the sigma bond between the hydrogen and the carbon breaks and the electrons come down to form our pi bond. As that's forming, we are going to then have the electrons from this sigma bond kick out with the bromine, giving us our leaving group, okay? So it all happens at the same time. That's why it's the E2 reaction, okay? So the base has to be there, it has to pull on the hydrogen, and then have those electrons kick in and have the leaving group kick out.
Structurally, does it matter which group it's first? Like,
Not yet, but yes, it will. Which beta hydrogen it takes off, there are going to be some rules associated with that. And we're going to talk about that later. Okay, we're actually going to talk about that in chapter 7. Okay, so because it's a 2 bimolecular reaction, it means our rate law depends on the concentration of the base and the concentration of the substrate. So if you change either one of those, you're going to change the rate of the reaction. Okay. All right, so that means our energy diagram is going to be nice and simple. It's going to be where we have one hump, we have one activation energy. The activation energy gets us to this transition state right here. We're forming this bond, we're breaking this bond, we're forming this bond, we're breaking this bond, all at the same time. So, we're good. The transition state here, we're forming this bond, we're forming this bond, we are breaking that bond, and we're breaking that bond all at the same time. Okay, so in contrast, the E1 is a unimolecular reaction, which means the first thing we're going to do is form a carbocation. Okay, so in this case here, we're going to basically boil our alkyl halide up in water here. And what's going to happen is it's going to first form its carbocation, and then the water is going to act like the base to remove a beta hydrogen eventually and give you your double bond. Okay, because it's unimolecular, we only care about the concentration of the alkyl halide. Okay, only about the alkyl halide. Okay, so our mechanism is, pretty simple. We have a slow step. The formation of the carbocation is the slow step because it's the hardest thing. We have to overcome that activation barrier to break that bond and form that ion. Now, the rules for carbocation stability still apply. Okay, tertiary carbocations are more stable than secondaries, and we hardly ever see primaries or methyls. Okay, so when we do this, we look at formation of the carbocation here. And remember that structure has changed. It's trigonal planar with an empty orbital top and bottom. Because of that empty orbital top and bottom, it makes it very easy for these electrons to kick in and form our double bond because there's already a little bit of hyperconjugation. So that proton that is right next to that p orbital is more acidic now because it's already donating part of its electron density to the carbocation. So that makes it very easy to pull off with a base. And so that makes this, easy to remove. Makes this easy to remove, and these electrons just flow in and form our double bond. Okay. So that means our energy diagram, because it's unimolecular, is going to have 2 humps. The first is our bigger transition energy, breaking of the bond to form our carbocation. The second thing that's going to happen is some base is going to have to come by and make it. Notice we're using water as a base in this case. In the other one, we used sodium hydroxide, a very strong base, or T-butoxide, very strong base. Here, we're using water. It's a very weak base. But because you already have the carbocation formed, that proton's really acidic, and we can use a weak base to give us our product, our alkene. So the first transition state here is the formation of our carbocation, and then our water comes in and acts as our base to give us this little teeny transition state to give us our final product. What do we notice about this energy diagram? It's endothermic. It's endothermic. Okay, so we went from a whole bunch of sigma bonds to 2 less sigma bonds and 1 pi bond. This tends to be an endothermic reaction because you have less of the stored energy from those sigma bonds with a less stable pi bond.
Will you ever see like an exothermic reaction?
You can. It depends on the leaving groups, but you can, yes. But in this particular case, it is endothermic.
So do you have to heat it for that to happen?
Yes. In fact, you have to heat it probably for a long time to get that first slow step to go. And then just form that carbocation. Once it forms the carbocation, the acid base step is fast. So, but yeah, you have to heat it. I mean, look how high the the delta G of activation here is, right? Okay, so how can we tell the difference between SN1, E1, SN2, and E2? Well, the first thing we need to look about is look at nucleophilic strength. Is it a strong nucleophile? Okay, does it already have a negative charge? Is it very polarizable? If it's a good nucleophile, it's going to do that first, right? Nucleophilicity is kinetic. So it's going to do that first. So if it's a good nucleophile, look for substitution reactions, specifically SN1. I'm sorry, SN2, because it's a good nucleophile. It doesn't have to wait, okay? Then you have to look at size. Once you get to size, like big and bulky T-butoxide, now it can't be a nucleophile. So it has to act as a base. So now we have to look at elimination. Okay, so size matters right there. And then temperatures too. If you do the reaction at a lower temperature, you can favor substitution products because it's kinetic. If you do the reaction at a higher temperature, you can favor elimination products because it's thermodynamic. Okay, so you favor elimination at higher temperatures, you favor substitution at lower temperatures. Okay. And then the most important thing, of course, is substrate, right? Like in the SN1 and SN2, we have the same kind of things happening here. Our tertiaries will do SN1 because they have to form the carbocation. Our tertiaries can also do E1 because it can form the carbocation. However, it can perform an E2. But you're saying, but why? I mean, it's a tertiary, it's sterically hindered. Well, we have to look at the beta carbon. The alpha carbon is the sterically hindered one, but the beta carbon might not be sterically hindered at all. And that's where we're putting the base. That's where the base is pulling the hydrogen off. That's why it can do an E2. Okay, so if you do a strong base like ethoxide or sodium hydroxide, you actually get E2 elimination from secondaries, as long as there is a beta hydrogen that's not too crowded. If your beta hydrogens are not too crowded, they can go there. So, but if we have a weak nucleophile or weak base, we actually get a mixture of SN1 and E1. In fact, it's such a messy reaction, you hardly ever want to do that. Because you're going to get, you're going to get a substitution, sometimes an alcohol, and you're going to get an alkene, and you're going to have this mixture always. Because you form that carbocation, the next step is the fast step. And so it can do either the substitution or the elimination. Depends whether the base came into the alpha carbon or it came to the beta hydrogen. That's why you get a mixture. Okay, so in secondaries, that's it. In secondaries, if you have a strong nucleophile or base, you're going to get the SN1 or E2 reaction. Okay, so if you had a good nucleophile, secondaries are going to go SN2. If you had a good base, it's actually going to favor the elimination product, the E2 product. And again, it's not sterically that hindered because we're looking at the beta carbon for where the base has to come in. We're looking at the alpha carbon in the substitution, but the beta carbon in the elimination. Now, if you have a very strongly hindered base, think T-butoxide, it only does E2. Again, we're not worried about the alpha carbon being crowded. The beta carbon is where your thing's going to pull off. And it's going to pull it off the least crowded beta carbon possible. Okay, now, in, of course, primary right here, it cannot do E1 or E2. Why? Because we can't form a carbocation on a primary carbon. They're just not stable enough. So that means we only have SN2 and E2. So if you have a good nucleophile, you get a SN2. If you have a strong base or a sterically hindered base, you get E2. Okay? So do we see why things are happening the way they do, right? Substrates control it, but the E2 reaction takes place on the beta carbon. So you still have to pay attention that you can do an E2 on the tertiary substrate. Okay. All right. So this actually is a summary chart for all of this. Okay, E1, E2, SN1, SN2. And it follows a trend. And I'm going to actually put an empty one of these on Canvas and have you try to work your way through it logically on how you're going to do your argument. So let's look at our first row here. Our first row, we have poor nucleophiles, methanol, water, acetic acid. Okay, not charged, but can act as a Lewis acid or Lewis base. In the case of our methyl primary and branch, or methyl and primary, we have no reaction. Okay, because it's not a good enough nucleophile and it's not a good enough base, nothing's going to happen. But by the time you get to secondary, you can get a slow formation of a carbocation. But then the fast step could be either substitution or elimination, so it's a mixture, always. So, and then tertiary, that will do an SN1 or an E1, a little bit faster because it forms the more stable carbocation. But again, it's poor things like water, methanol, acetic acid. You see that as your only reactant, think unimolecular reaction, think carbocation. And what are my two products possible? So let's say we had water and we had a tertiary alkyl halide. What are our two possible products? Well, we can make an alcohol using the water as a poor nucleophile after forming the carbocation, or we can make it the alkene. So you're going to have to write the alkene and the alcohol as your two products for the tertiary alkyl halide in water or methanol. Methanol would give an ether, by the way. Okay, so let's look at the next thing. Weak base, but good nucleophile. Okay, so things other than hydroxide and alkoxide that have a negative charge, right? All SN2 until you get to tertiary. And then you go back to the carbocation. So that makes sense, right? Good nucleophile is going to do a substitution reaction preferably. Okay. Now, what if we had a strong base, but an unhindered base? We're thinking methoxide, ethoxide, hydroxide. Okay. So now the methyl can't make an alkene because there's no other carbon, there's no beta carbon. If there's no beta carbon, we can't make the alkene, we can only do the substitution. Okay. Now, if we have a primary and it's unhindered, then it can do SN2 reaction. But if it starts to get crowded, it starts to have more of those beta hydrogens available, it does an E2. And then the secondaries and tertiaries always do E2 when you have a strong base, a strong, small base. Do we see why the first two actually do substitution reactions? Why these two do substitution reactions? Because they're unhindered in the substitution. As soon as we start getting any hindrance to that, it goes to the beta hydrogen and does elimination reactions. Now let's go to a strong, unhindered, hindered base, like T-butoxide, okay? It actually will make an ether with an SN2 with the methyl because there's no beta hydrogen. It can't do the elimination. But everything else does an E2 because it's non-nucleophilic base. It's going to pull off that hydrogen. Which hydrogen? The alpha hydrogen or the beta hydrogen? Beta hydrogen. It's going to pull off that beta hydrogen. All right. So I would go through this chart, rationalize to yourself why each of these boxes are filled in this way. Okay. All right, so that is the end of chapter 6. And this is chapter 7. Let's go ahead and take roll. All right, So chapter 7 is a continuation of what we were just talking about. We're going to talk about those elimination reactions. We're going to dig into them and get some rules as to which ones, which is the primary thing is going to form. But let's first start with nomenclature. Okay, when you only have two groups on an alkene, we learned we can call them cis and trans. If they're on the same side of the alkene, we call them cis. If they're on opposite sides, they're trans. Okay, but when we look at if you have more than two groups on there, you have to figure out which has higher priority. Luckily, prioritization is based on the same rules we use for chirality. So number 1 is Z number. Number 2 is what's the difference as you move out. 3 is double and triple bonds. 4 is isotopes, right? So in that case, if we have the two groups, so let's look at this one right here. What we do is we look at each carbon of the double bond and we decide which group has the highest priority. So in this case here, the hydrogen is going to be lower priority than the oxygen, which makes the OH the higher priority group on that side. Then we look at the other side and find out this is a methyl group, this is an ethyl group, which makes this the higher priority. Okay, so now we have two things that are, we know exactly which two things have the highest priority. And when we look at which side of the double bond they're on, they're both on the same side of the double bond. So we actually have a new name for this. We call it zusammen. Okay, zusammen is German for same or together. And the way you can remember it is Z groups on the same side is zusammen. So zusammen is the equivalent to cis if you only had two groups on your alkene. Okay. Now, on the other end, right here, since our primary, our two groups are on the opposite sides of our double bond, we look at it as entgegen, which means opposite, and so, or E. So you just have to write the Z or the E. And just like R and S, it comes at the beginning of our name, always. The stereochemistry is always the first thing in our name, okay? So let's practice that a little bit right here. So on this one right here, we have a bromine, a methyl, a chloro, and a hydrogen. So that means the bromine and the chlorine are our two highest priority groups. And so we want to look at our first carbon. What is it? Yeah. We want to look at our first carbon first and say, okay, this one's our highest priority. We're going to look at our second carbon with a double bond. We're going to say that's our highest priority. And our two highest priority groups are on opposite sides of the double bond. So what is it, E or Z? E. Right
So
there.
when you look at sides, like you kind of look at it in ways like as a cross.
Okay. The way you want to look at it is if you take, you look at each atom, each bond, each carbon of the double bond. Look at this side first, then look at that side and determine that, and then say imaginary line through your double bond. Are they on the same side of that double bond or on the opposite sides of that double bond? Okay. So we're looking at each group and then we're looking where the double bond is. Okay. So in this case here, chlorine is the higher and then the ethyl group is higher. So we're having our imaginary line here. And so they appear to be on opposite sides. So it's E. So this is pretty easy. Let's see, we had to do our prioritization with the chloro here. And there's a chlorine way out here, but we had a carbon attached. So this makes our highest priority. The oxygen makes this higher priority. So that gives us our opposite side, which is our Z. I'm sorry, they're on the same side. Same side, Z. And just like here, our two higher priority groups. Wait, that's wrong. Chlorine is higher priority than oxygen. That's not the highest priority group there at all, is it? So, but this carbon is higher priority than that carbon. So that means they're on opposite sides. So it's E. Okay, do we understand E and Z?
Yeah.
It's a lot easier than R and S, but it's important. Okay, so we've already done that. So now let's talk about stability of alkenes. I said we're going to have some rules to which product are you going to form. It turns out it's going to be a thermodynamic reason, and the reason is that we have stability in alkenes changes by the number of groups that are substituted. terminal alkene is basically that. It's at the end of the chain. So you can think of, if we just drew hexene right here, it's with the double bond at the end of the chain. It's supposed to be a double bond. Double bond right here. So we have 1, 2, 3, 4, 5, 6. So this is what we call a terminal alkene. So it's at the end of the chain, okay? An internal alkene is it anywhere else inside. There has to be at least one unhybridized carbon on that double bond. So this one down here is what we would call a internal alkene, okay? So turns out internal alkenes are more stable because of the more substitutions. Not only that, but if we just have two substitutions and we're comparing two alkenes together, turns out trans alkenes or E alkenes are more stable than Z alkenes. Why?
Because they're balancing the polarity.
Nope. We have the two groups here are starting to butt up into each other and they're trying to press out. So it's a sterics thing. Thermodynamically, they should be the same, but we have sterics pushing these out, giving us.
Wait, so that one's more stable?
This one is more stable.
Okay, that's
This is less stable. Okay, and it's less stable because of that pushing those groups out is straining that double bond a little bit. And that gives you that difference. So that's two ways to see which something is more stable. If you looked at them, terminal alkenes are less stable than internal alkenes. And then E alkenes, opposites, are more stable than Z sames. Okay, but there's even more information here. Okay, so we don't just make it up or say, oh, well, you know, the model looks better or anything like that. We actually do an experiment called the heat of hydrogenation. So basically what we're going to do is we're going to take our alkene, we're going to add hydrogen across that double bond, and the amount of heat it liberates tells us how much energy was stored in that double bond. Okay, so the more energy given off, the less stable it was. Does that make sense? The more energy it gives off, the less stable it was.
How does that?
Because let's say if you add hydrogen across the double bond and it only gives off 1 calorie, right? So that was a pretty stable double bond. Now let's say you have another one and you do it and it gives off 10 calories. Okay, so that means it gave off more energy. That means it had more, it was less stable than the one that gave off 1 because it only went down
So
1.
it's using the energy to attach the hydrogen, or what is it using the energy for?
It's the heat liberated during the hydrogenation.
Oh,
It's the heat liberated during the hydrogenation. Okay, so it gives off a certain amount of energy. Okay, so that means the smaller, the lower the energy, the more stable it is. So if we looked at a terminal alkene here and we did our measurement, we found out it takes about it liberates 127 kilojoules per mole. But if we just moved it to an internal alkene that was cis or Z, it actually takes 7 kilojoules per mole less energy. It liberates that much less energy, meaning that that was more stable. The internal double bond was more stable. And if we go to the E or opposite right here, it gives off even less. It gives off 12 kcals per mole less than the terminal alkene. So by measuring the differences in these heats of hydrogenation, we actually get a stability of which things are much more stable. Okay, so using this kind of data, we actually found out some really cool stuff. Okay, it turns out that, let's go back to hybridization again. You know, the more percentage of your S character here, the more able you are to accept electron density, right? Because the S is smaller, held tighter to the core, so it can accept that electron. sp3 carbons are more able to donate electron density because it has less s character, more p character. Okay, so what does that mean? That means the carbons adjacent to your double bond, your beta carbons, can donate electron density to your double bond, just like in the stability of a carbocation, right? So if you only have one thing or no carbons next to it, you have an unsubstituted alkene, and that has to be the least stable alkene we can have, okay? Because it's a terminal alkene and has no carbons to donate any electron density to that double bond, okay? Now, by just adding one group, it gets more stable by almost 2 kcals per mole, okay? By adding 2 groups cis or 2 groups trans, we're able to see that they have different stabilities. The trans is more stable than the cis. So we actually measured it. It's not just saying, oh, they're butting up against each other. We actually measured it to show it's more stable. Then this with the 2 carbons on one side is just a little bit less stable than them on opposite sides. Why? Because the 1 carbon only has hydrogens. The other carbon has 2 carbons that's pulling some electron density, but the other side does not have any carbons to pull electron density to it. Therefore, it's not as stable as having 1 on each side to pull in electron density. And then, of course, by 3 and 4, you get to even more stable. It's the most stable you can have. So a tetrasubstituted alkene is the most stable alkene we can have. So that's going to tell us about which products we're going to make, right? When we're looking at our alkenes, which beta hydrogen is going to be removed. We're going to be driven by that stability. Okay, so let's look at our 2 different ways to make alkenes. They're both elimination reactions, okay, but they just have different leaving groups. In the first one we talked about a lot was the dehydrohalogenation, where we're removing a halogen and a beta hydrogen to give off, basically using a strong base. And so we did that already. And then we're going to talk about another way to do it where we used heat, and we call it dehydration. So we take an alcohol and we add acid to it as a catalyst, and we're going to make that alcohol a leaving group, and then we're going to do that same kind of elimination. Okay, so let's dig a little bit into that. So we looked at the dehydrohalogenation just today, so that should be fresh in your mind here. Most of it's, the best ones are the E2s. You're just looking for your beta hydrogen and then get your elimination with your alpha carbon there and get your product here. Now, we went over these rules right here, but this is a nice good rundown when you are studying for your quiz, that this is a good thing. We want to look for, strong non-nucleophilic bases to prevent our SN2. If we use a strong base that can be nucleophilic, we might get some substitution products. But if you run the reaction cold, you'll get substitution products. If you run the reaction hot, you'll get elimination products. So you might want to look for the temperature used when we see that. But cheap butoxide will always give elimination products in anything other than a methyl. Okay, so let's talk about the regioselectivity. We talked about where is the double bond going to form, okay? So we actually have a regioselective reaction because we want to form the more stable alkene, okay? So it's going to selectively choose the beta carbon that it's going to pull that hydrogen off based on which product is going to be more stable. So the more substituted alkene is going to be formed. So let's look at these 2 possible pathways here. In both cases, we're going to use a strong base, hydroxide, and we're going to use it with, it's in a tertiary alkyl halide here, so we don't have to worry about substitution reactions. So it's only going to do an E2, okay? So we have a possibility of our 2 beta hydrogens here, and then we have another possibility of our 3 beta hydrogens here and 3 beta hydrogens here, which are the same, okay, right? So we have 6 beta hydrogens that are on methyl groups, and then we have 2 beta hydrogens that are on that carbon with a CH3 on it. Okay. So if we were to come in with our base and get our transition state to come out to the beta 1 carbon, the outside one, we're going to end up getting a terminal alkene, right? Because we had a methyl group here. We're going to use this methyl group. That's going to give us a terminal alkene and give us our product here. Okay. Well, you know, it's an alkene. It's disubstituted, but it's terminal. But what if we instead looked at taking one of these hydrogens instead? So our transition state's a little bit different. We're actually having our base come in. Again, it's not too crowded because it's the beta carbon that we're looking at. It's going to pull off this hydrogen here, giving us our double bond here. Now, this is tri-substituted and it's an internal alkene. Two things to tell you, it is more stable. Okay, so this is actually our major product right here. Because we have, this group isn't that big, and so we can get to that internal alkene, the more stable alkene. Does that make sense? All right, so let's look at why it's so regioselective. It has everything to do with the transition state. The transition state on forming this is we're going to have our transition state with the beta hydrogen that gives us our internal alkene is actually lower in energy than the one that gives us our transition state with our terminal alkene is a higher. Okay, so because that has a higher energy transition state, it goes slower. And they're not very different, but they're different enough that there's going to be a different product ratio. That's why you still get both. It's still low enough that both can happen, but one's going to happen faster than the other. And the reaction that happens faster gives you more product. So that's why we see our transition state for the less substituted one takes more energy to get to. So it's slower reaction. Okay. So let's talk about substrates. When we have a SN2 reaction, we saw that the halogenation, the primaries went much faster than the secondaries. The secondaries went faster than the tertiaries, but the tertiaries would, almost not even go SN2, right? Well, it turns out for E2 reactions, it's the opposite. The tertiary goes faster. And part of that reason is that we get more substituted alkenes in our tertiaries than in our secondaries and our primaries. So we actually have a faster reaction. So, which is really kind of cool because that makes our elimination reaction faster than any substitution reaction for our tertiary systems. But we have to worry about on our primaries that, oh, it's going to substitute. It's not going to be. So let's go back to that chart we talked about at the end of the last chapter. You're going to see that methyl group is going to do an SN2, but the secondary, as soon as it gets with a strong base, it's going to start doing E2. We're going to see because the rate of the E2 reaction is picking up. And so it's going to go faster than the SN2 reaction, and therefore it's going to give you the elimination product. Okay. So let's talk about the different possibilities of stability here. So in this case here, we have a primary alkyl halide right here. Oh, sorry, I gotta sit down, my foot hurts. We have a primary alkyl halide here. And when we look at our beta carbon here, right here, we're going to come in with our strong base and it's going to give us a terminal alkene. Okay. So our primary here gives us a less stable alkene. Okay, there's no option for us to make that an internal alkene. Okay, by the time we get to a secondary, if we move this over here, we have an opportunity to make an internal alkene. When you get to the tertiary right here, you always will get at least a disubstituted alkene, no matter which carbon you remove from, because that your double bond is going to form between two of those carbons, giving it disubstituted, making it more substituted and more stable. Questions on that? Okay, so let's start predicting the major product of our E2. Okay, you can ask your question now. Which way is it going to go? So now this is our question. We actually have a rule for this. We call this Zaitsev's rule. Zaitsev's rule says that you will always get the more substituted alkene as your major product. You will always get your more substituted alkene as your major product. And it has to do with the idea that it's the more stable product. The more substituted it is, the more stable it is. The more stable it is, that's going to be your major product. So in this case here, we have some options. On our beta carbon here and beta carbon here, we got 4 of those hydrogens available to us. And on this beta carbon, which is different, we have 3 beta hydrogens that are available to us. Now, if we have 3 there and 4 there, if we do it with the beta hydrogens over here, we're going to make a di-substituted alkene. Okay, even though it's a tertiary alkyl halide, we're going to make a di-substituted alkene. But if we were to instead take it from here, we'll end up with a tri-substituted alkene. So if this is taking it from the beta 1 carbon, we get the major product, the tri-substituted alkene, 1, 2, 3. And if we took it from this beta 2 hydrogen, we would get this di-substituted alkene. Therefore, this is going to be our major product because it's the more substitute. In fact, what you can do is when you do the homework for this, which I've extended till Friday, by the way, I've extended till Friday. When you're asked to do this, draw both of them and then determine which one's the most stable. And then that's going to be your major product. Okay. Okay. So in the case of our reactivity here, our tertiary alkyl halides are more reactive because they're going to give at least a secondary or tertiary substitution pattern. Alkyls are only going to give a di-substitution, secondaries, and with primaries, you're only going to get mono-substitution. So they go slower. They make less stable products, so the reaction goes slower. All right. Now, the only thing that breaks Zaitsev's rule is conjugation. Okay, if there is a place, if there's already a double bond or a benzene ring near in your alkene, your alkyl halide that you're looking at, you will actually not form the more stable product by forming the more substituted alkene. You form the more stable product by having your double bonds in conjugation. So what you're looking for is double bond, single bond, double bond. You're going to want to make sure that your new alkene you form is in conjugation with the one that's already existing. So for example, in this case here, you're like, well, you know, if I do this one right here, it's going to give me 1, 2, 3 substitutions. Okay. But it doesn't form that as the major product, because if we take this hydrogen off here, one of these hydrogens off and form the double bond here, we have double bond, single bond, double bond. That's more stable than the tri-substituted alkene it would have formed. Okay, so when we see this double bond, single bond, double bond, you want to have that as your major product, because that's a conjugated diene, and it is more stable because of that conjugation. Think about it. This is a lone pair. I mean, sorry, these are p orbitals. These p orbitals can overlap and conjugate through there. So that's why they want to be in that configuration, and that's why they're more stable than if there weren't. So here we have a double bond, single bond, single bond, double bond. So they're not in conjugation. There's a whole sp3 hybridized carbon in the middle. Okay. So this also takes case in the case of benzene rings, because remember, we have those p orbitals here. And so the pi bond wants to be in conjugation with the p orbitals on the benzene ring as well. So double bonds or triple bonds or benzene rings will all break Zaitsev's rule, okay? It's probably almost the only time you break Zaitsev's rule is when you have conjugation. Okay, questions on that? So Zaitsev rule says you form the more substituted one as your major product. Okay. So we can actually kind of play with the mechanism a little bit by changing our base, okay? So in the case of this, we have a tertiary alkyl halide, and we have a small base right here. So gosh, it could almost act as a nucleophile, but it's a tertiary, so that's not bad. So it probably won't act as a nucleophile, but we've heated it up. What does heat do? Heat promotes the E2 reaction. Heat promotes elimination reactions. So we're going to see elimination products as the most common products here. So we have a choice of our beta hydrogens here or our equivalent beta hydrogens here. Okay. So are we going to do the ones on the right or the ones on the left? Well, the ones on the right here is going to give us our more substituted double bond. Because it's giving us our more substituted double bond, it's going to give us our major product.
So why is that giving you more substitution?
1, 2, 3 substitutions. This one only has 1, 2 carbons on its out double bond. So it's less substituted, less stable. Does that make sense? So you can get both products, but you're going to get your major product is always going to be your more substituted product. Okay. Now, if you have a really big bulky base, what you can do is you can actually force it to do the least hindered side. Okay. So when you have a small base in heat, follow Zaitsev's rule. When you have a big sterically demanding base, T-butoxide, the T-butoxide can't come in and get close enough to this. So what it's going to do is it's going to take one of these 6 hydrogens way out here that aren't sterically hindered. And we actually switch it, getting to our less substituted is our major product, entirely because of the size of this T-butoxide. Right here, it can't fit in here, so it has to grab one of these 2 beta hydrogens. Okay. So when we have it break Zaitsev's rule because of a big base like this, we call it the Hoffman rule. The Hoffman rule. So Zaitsev's rules work for most of your things except for conjugation. And when you look at T-butoxide, double check your reactions when you look at T-butoxide. Okay. So then let's see. We also have the possibility of having a stereoselector reaction by whether or not it forms the E or the Z. Okay. So just from what we know about stability, which do you think we're going to form most of the time? E, because you want the 2 large groups opposite each other so they're not butting up. So in the case of our stereoselectivity, if we have 2 big groups like this here, we have an opportunity of creating, eliminating one of the hydrogens will give us one of the isomers, the other hydrogen will give us the other isomer. And because we're using our base and heat, our trans alkene, our our E substituted product here is more stable and therefore is our major product. Our Z is less stable and gives us our minor. It still gives it, but I said, what if we pull off one hydrogen, it gives us one, and if we pulled off the other hydrogen, it gives us the other. How? Does that make sense? How? It's an E2 reaction. It happens all at once. It's a concerted reaction. So what makes that happen? Well, because it's a concerted reaction, we have our transition state where we want to have the base pulling off our hydrogen, leaving those electrons are kicking in, and then the electrons that are going to kick out have to be anti to the electrons coming in. It makes it more stable. Okay, so that means when we arrange our system, we want to have it such that we have, let's say we have a big group here, and a big group here. In this case here, we have the two large groups are anti, and the hydrogen and the leaving group are anti as well. Okay, so we have both of them are anti, and we have these two groups here. So let's say if I wanted to pick off the other hydrogen instead. Okay, so we're going to leave this group back here because that hasn't moved. But let's say I wanted to take away this hydrogen there. Okay, and we still had our big group here. Okay, can it leave? Can that hydrogen leave right there in this configuration? No, because it's not anti to our leaving group. So we would have to rotate that around and get our big group here, our hydrogen we want to leave here, anti to our X here and our group here. So now, by just removing the other hydrogen, this one on this side, we have to rotate it around till the two groups that are leaving are anti, the hydrogen and the leaving group here. When they're anti, you can form that double bond and you end up with the Z product, okay? So when I said you remove one, you get one product, you remove the other, you get the other product, I wasn't lying, it's true. You just have to look at your Newman projection to see which side they're on to give us that reason. All right, questions on that? So your transition state controls whether or not you get the E or Z isomer. But you always have to have those anti-periplanar, or they need to be anti to each other. Okay. So there is a possibility of what we call Cis elimination, where you have them in this configuration here. It's not as favored because the transition state is your electrons are coming in and going out at the same time, and you're in that eclipsed condition during the transition state. So while it technically can happen, you might get a little bit of product from that. You're most likely going to get your anti-elimination product as your major product, and your anti-elimination product, if you have two groups, being anti to themselves, as well as being anti between your hydrogen and your leaving. All right, questions on that? Okay, so let's look at the stereoselectivity of this product here, okay? If the reactant has only one hydrogen on a carbon that the hydrogen could remove, what would the dominant product be? Okay, if it only has one hydrogen, you have to rotate your bond until you get to where your hydrogen is anti to your bromine. So in this case here, we would have to look at I'm going to look at it from this direction here. So our hydrogen's up on the top. We have a CH3 on this side. We have a phenyl group on this side. That's a benzene ring here. And then in the back here, we have our bromine down and our methyl group up and our other hydrogen here. So that means it has to be in this configuration in that transition state. When it's in that transition state, the two methyl groups are on the same side and give us this as our major product. Okay. So, but if we had the different isomer right here, we again would draw a Newman projection. We have our up there, our CH3 is here, our benzene ring is down here. Look at our back side here, we have our hydrogen, we have our methyl group, and we have our bromine down here. So that means that we're going to have the phenyl and the methyl are going to be on the same side in the final product. Okay. So drawing these Newman projections and getting the two leaving groups anti-periplanar to each other is the best way to get the correct isomer of your product. Okay, questions on that? So in both of these, because there's only one hydrogen, there's only one transition state possible, and therefore there's only one product. No, I have 15 minutes. All right, so let's look at that a little more intensely right here. So what we're going to see here is that even though you have a couple options to get this, notice how the two large groups are anti to each other, and we have our two leaving groups as anti-periplanar. This is going to give us our best case scenario for having our transition state have the lowest energy. Lower energy makes it the higher product, higher formed product. So in the case here where we have our two groups here, they're gauche. That's not as stable as if they were anti, as the ones on the right. And therefore it's going to give us our product here is going to give these two on opposite sides of the double bond, giving us our trans isomer in this case. And these, the double bond is going to form here, and they're going to be locked in on the same side again. Okay, so we have rules on where to make our double bond, right? If we're not using a bulky base, we can use Zaitsev rule. Okay, if we already have a double bond in there, we have to break Zaitsev rule when we want them to be in conjugation. If we're using a big bulky base, that's Hoffman's rule. You go for the least hindered beta hydrogen that you can get because of the big bulky group. So those are our three rules at forming this. And then our other rule we have here is our leading groups need to be anti-periplanar to each other. So look at your Newman projection and see what your final product is. All right. So let's do a few examples. Okay, so let's just look at that one for a minute here. So we have a secondary alkene, alkyl halide right here. And so we can form a double bond over here, or we can form the double bond over here. Okay, so let's get more information. What's our base? Okay, is that a big bulky base? No, it's a pretty small base. It's methoxide and ethanol. So it's going to follow Zaitsev rule or Hoffman's rule. Zaitsev rule. So we're going to form the double bond here as our major product because it's small enough to come in and take the beta hydrogens from that internal carbon. Okay, so what we see here is that we have our internal double bond is our primary, and our terminal double bond, our terminal alkene, is our minor product. Notice you always get a little bit of both because, you know, it's where, you know, in the transition state, there's not that big an energy difference. So it's favored, but doesn't completely eliminate the other one. Okay, so let's look at this one again. Let's look at this one now. Again, small base, so we're going to try to follow Zaitsev rule. So we could make a double bond here, right? No, we can't make a double bond there. Why? There's no hydrogen. There's no beta hydrogen, so we can't make a double bond. Okay, so that means we got to erase that because we can't do that. Okay, so where can we make a double bond? Well, we can make a double bond here because we have beta hydrogens. So we could do that. Or we can make a double bond here because we have beta hydrogens. Okay, so just by looking at that, which is more favored? Probably the one that's going to give us the internal double bond. So it's going to be the major product. Okay, so our major product is going to be the double bond internal, with our minor product being the double bond. Well, not only is it there, we also have to think about which side is which on here. So we want to make our double bond here. So now we have to figure out where the two groups are right here. So we have to draw our transition state to figure out our major product. So let's draw this carbon first. So we're going to do hydrogen, hydrogen, oops, hydrogen, and CH3. And then we're going to draw our back one, and we're going to put our T-butyl group way over here, which puts our bromine here, which puts our methyl group here. Okay. Why did I put my T-butyl group way up there? The T-butyl group is on the side with the hydrogen. That's the least interaction it has. So when it forms this double bond, it's going to make the two methyl groups on the same side and the T-butyl group and the hydrogen on the same side, right? So that's going to give us this product. That's our major product. Ooh, potential span. Yeah. Oh, okay. All right. So if we draw the other one, the other possible state we would have to have the methyl group on this side, the hydrogen on this side, the other hydrogen on this side, the T-butyl group here, the methyl group here, and the bromine here. In this case here, we have the methyl group and the T-butyl group are getting close to each other. Therefore, when we form the double bond, the methyl group and the T-butyl group would be on the same side, which they were on here. So that's why it's the minor product, is because of that transition state right here. Okay, questions on that? Okay, so elimination reactions, we follow some rules, okay? We look for the base, we look for the temperature of the reaction, we look for the substrate. Then the next thing we look for is our beta hydrogens. Where are they? Which ones are going to give us the most stable product? Zest Rule. If you have to do conjugation, then you do conjugation. If you use a big bulky base, use Hoffman's rule. Okay, questions? Okay, still have some time. All right. So now let's look at cyclohexanes. Now, the reason I like to look at cyclohexanes is it kind of forces you to do exactly what we were doing before, looking at those Newman projections. Okay, because in the case of cyclohexane, well, you can go, from chair to chair. There's only there's no way for you to do a free rotation. Okay, so if we look at this right here, we have a possibility of doing, this is a beta hydrogen, and this is a beta hydrogen. And I'm going to draw this hydrogen here, because there should be a hydrogen there. And we have this beta hydrogen. Well, let me change colors. We have this beta hydrogen and this beta hydrogen. Okay. Now, one of those two sets is favored over the other. Okay. Now, anybody want to hazard a guess here? This chlorine is not anti to that hydrogen or anti to this hydrogen. These two hydrogens are anti to each other, and this hydrogen is anti to the carbon over here. So can we eliminate one of the blue beta hydrogens? The beta hydrogens over here. We can't eliminate either of these hydrogens because neither one is anti to the leaving group. Okay, now let's look at the other side here. Neither of these hydrogens are anti to the leaving group chlorine.
So they can't leave.
They can't leave. Okay, but let's look at the other two. If we look at that, we have this one is not anti to this chlorine either, and this one's not anti to that. So that's going to make it very difficult to remove. So we need to have, oh, actually, this is an anti. This is anti to that. Yeah. So when we look at this, when we try to do that, we can't eliminate in this configuration. There are no anti-hydrogens in that boat, in that chair configuration. So what we have to do is we have to flip it to the less stable chair configuration. Why is this the less stable chair configuration? Because the chlorine is in the axial position. The chlorine is the biggest group. The biggest group should be in the equatorial position. So now that it's in the axial position, we actually have this hydrogen is now anti to that. This hydrogen is now anti to that. So what does that mean? both sides can react, but it can't react in chair 1. It can only react in the chair 2. And this conformer is less stable, and therefore this reaction is going to go slower or faster. The other one, slower, because it spends less time in this configuration. It can only eliminate when it's in its least stable
It doesn't
configuration.
make sense if it's less stable. It's gonna go slow.
Well, because there's less, imagine, let's say you have chair 1 and chair 2, right? It's in chair 1 90% of the time, it's in chair 2 only 10% of the time. It only reacts in chair 2. So only 10% of the available material can even react with the base. So if only 10% can react, it's going to slow the reaction down. It has to wait until I go from my chair 1 to chair 2, then I can react. Chair 1 to chair 2, then I can react. It'll all go eventually, but it's going to be slower. Does that make sense? All right. Okay, so that's one more slide. Okay, so this is what we're saying here, is that in this condition, the equatorial chloride is not going to eliminate. It is no reaction. It has to go into its axial chloride here before it can react, and then it can react. It'll give, and then it gives the simple alkene, cyclohexanes. Okay. All right. And I think this will be my last slide here. So now we have to, when we think of these, when we draw these, if we have multiple substitutions on here, you might actually have a substitution so big that you might not get an elimination at all. Okay, so we have to think about where the different chair and which is the most stable system. So in theory, this is the more stable one. This is the more stable one because our two groups are both in the equatorial position. Even though our chloro is in the axial position, it's smaller than the two other groups. So that means this is going to be more stable because our two biggest groups are axial or equatorial. And when this reacts, it's going to give us this product because this is our anti, this is the hydrogen that's anti to it. So it's going to give us our more substituted, our tri-substituted alkene. Now, if this were to react, oh wait, this can't react. There's no hydrogen. It's anti to it. Those hydrogens are not anti to it, so that can't react. So so what does this mean? That means we only get one product. We get one product from this reaction right here. Now, if we changed up put the chlorine on the equatorial position, we'll actually get a different product. Because when the chlorine's on the equatorial position, it has to go to the less stable to get to this axial hydrogen and the axial chloride here to get that elimination and transition. And we actually get the less stable alkene. But it's the only beta hydrogen we have available to it because it's the only one that's anti to the leading. Okay? All right. Let's see, I think I have one slide. Okay. Okay, so this is my last slide for today. But what you need to look for is go through your chair 1, chair 2, try to figure out which is more stable. And then you have to get it so your chlorine and a hydrogen are in axial positions to do the elimination. And then that determines the isomer you get. And that determines where the double bond is. Yes.
So is there no scenario where chlorine is equatorial and an elimination can happen?
No, because the carbon on the ring is anti to it. If you do it that, if you make the structure, you'll see that the chlorine is going to be equally anti to a carbon in the ring when it's equatorial. You can only do it when it's in the axial position. So
Both the hydrogen and the chlorine.
correct. And they have to be opposite each other. Yeah. So if you actually take this right here and draw a Newman projection from it, you'll see that in the equatorial position, it's anti to the carbon in the ring. And in the axial position, it's anti to a hydrogen. And you can eliminate it. Okay. All right. Thank you. We'll go with the rest of it on Wednesday after the quiz. quiz up to this slide. Learn Zaitsev rule, Hoffman's rule. Oh, yeah. Practice those Newman projections because that'll really help. All right. Anybody there? Okay. Okay. I'm going to stop sharing and stop recording.